So today in this video we're going to talk about the logistic regression. So in the previous two videos you already have covered the fundamentals with respect to the linear regression, how the cost function is being optimized by using gradient descent, and as well as the other variant of a gradient descent called a stochastic gradient descent. So here we're going to talk about how the regression algorithms can be tweaked so as to do a classification kind of a problem. And here we're going to talk about logistic regression, where the same principles are being used for the binary classification problem. So when I say binary classification problem, what we actually mean, so let's say this is logistic regression, and we wanted to predict whether a particular we have some data about let's say a student, right? Some student data like age, height, weight, and all those stuff, and we wanted to predict whether this student belongs to class 1, or let's say class 2. So this is a typical example of a binary classification problem. And what it does, if you this logistic regression, it spits out a probability of of this event of the student being into one of these class as into the probabilities, right? So let's say if the model says that for this student, let's say id equals to some 1, he or she belongs to, let's say, this probability is 0.8. So what it means is that the model thinks this student with id 1 with all those input features belongs to a class 1. Similarly, for let's say another id 2 or something, the model says that this is basically 0.2, right? Now if you the fundamentals of the probability, that sum of the probabilities of an event is 1. And since here we are talking about only two of the classes, that means there are two probabilities. So that means if this is 0.2, then obviously it is 0.8, and hence we can say this id2 student belongs to class 2. So this is the interpretation side of the logistic regression. Let's also do the maths behind it, and how we are actually using a regression algorithm for for doing a binary classification, um, for solving a binary classification problem, right? So the nutshell, or the in the fundamental nutshell behind the logistic regression, is basically a sigmoid function. And if you look into the curve of a sigmoid function, let me just quickly change the um, you know so it is something like this, right? And this actually goes to minus infinity, and this is infinity, and in between we have the zeroth uh, axis. So this is the response of a sigmoid function. And what we do is that we use this sigmoid function, we feed the values, and then we like convert the whole thing into something called as a logistic function. Now what logistic function does is that it actually spits out the values between two different values. One is the 0, another is the 1. So the values belongs to between 0 and, so this is the lower bound, and this is the upper bound, right? Okay. So if I now rewrite the equation with respect to sigmoid function for logistic regression, it would be looking something like this. We write stick r, it will be something like 1 plus e to the power minus z, where z is basically the, it's very similar to what we have seen with respect to linear regression. So these are the coefficient attached with all those features x1 and x2. And this log r is basically a log of odds ratio. So we can also rewrite this equation to something like this, something like this actually, and so on. Now this is basically, it's called as a log odds ratio, right? So what it actually means is that, let's say event here, like we have this event of a student belonging to class 1. So it's basically the ratio of an event belonging to class, let's say 1, by class 2, right? So if you see, the logistic regression is basically a linear regression kind of a problem. The linearity is still intact, whereas what we are doing is we are just converting the whole output in terms of 0 and 1 by using the logistic function, which is the a kind of a sigmoid function being used and under the hood, right? Now if I talk about the cost function, so obviously in the if you look into the linear regression problem, we have the cost function, which is the mean square error, and this is actually pretty simple, which is square root difference between the prediction and the actual and taking an average of it, right? But in this case, since we are dealing with the probabilities, so we cannot use the MSE as a whole, because if you see, the difference between the probabilities, I mean the probabilities of classes will be extremely lower, and it becomes very hard to be stored in floating point numbers. And so what we do is that we have something called as a log loss, right? So if you look at the log loss is basically nothing. It's basically a negative average of the all the observations being taken into concern across the training data set, and it will be looking something like this. Again, sum from the first till m, it will be y for all the ith instance pi plus 1 minus 2 of 1 minus pi. So how it actually works, let's say the y actual is 0, then the log loss cost function, it becomes something like this. um, so this is 0, 0 into this term, so this also becomes 0, plus 1 minus 0 log of 1 minus p1. Now if we just put this all together, so it will be sum of log of 1 minus p1 for y equals to 0, right? And the same thing, if I have the y a actual is equals to 1, so the log loss, it will be 1 minus m. So we can just put it here, 1 into log of p plus, now here 1 minus 1 will be 0 again. So similarly we can replace the whole thing, very simple, like something like this, right? So this is the cost function with respect to the when the y value, actual value is 0, and this is when the value is equals to 1, right? So so this is actually the cost function being updated. And if I just write the partial derivative output, it will be looking something like this. We'll take a m, and the summation from I equals to m, we take a sigmoid of the cross the dot product of this minus y for the jth instance, right? For the jth feature, this will also be. So this is the the equation we have, partial derivative equation of the cost function for the jth feature. So we already have seen the cost function with respect to the different classes, like here when the y belongs to 1 and when y belongs to 0. And if you see the graphical response for the each classes, let's say this is the y belongs to 0 class. So the response will be something like this. Let's say this is 0, this is 1. So and this is the cost function, right? So as we move away from 0, the cost function is basically increasing, right? And it goes all the way to infinity. Same thing if we have, if we have the y belongs to, let's say y belongs to 1, the responses will be exactly opposite, in which it will be basically decreasing. This is 1 and this is 0, and this is same cost function, right? So as we move from 0 to 1, the cost function decreases. So these are the two different responses of the same cost function, with respect to the, what classes a particular sample belong to, right? So this is what we have with respect to theory, right? Another thing we wanted to understand is the decision boundary, that what will be the values in which, a model will tell, where we want to tell that a particular sample belongs to class 0 or class 1. So if, the value of is basically, we can actually represent something like this, that if p is less than 0.5, then we say the y is basically 0, and if the probability is greater than equals to 0.5, then we can say y belongs to 1. Okay, so here's a little bit of silver lining here, that if the probability is basically 0.5, in which the output is kind of random, we are not sure whether, the sample at 0.5, whether the sample belongs to, the 0 or 1 class, and here we have some random decision boundary, we are not sure about it. So what we wanted to have is always to make sure that the model has some value, lesser than 0.5 or higher than 0.5, so as to make sure our model is not randomly putting some BS stuff, right? Cool. So let's quickly jump to the coding side, and we want to try out, different combinations. We also try one of the famous cancer dataset, and we'll compare the results. So in the coding side, let's jump on the coding side. I'll quickly import the required libraries. So we'll be needing the NumPy. We'll be needing pandas. So learn. We'll be dealing with the breast cancer dataset. So breast cancer dataset is basically, it's a very famous dataset where, with some of the features we put into the model, like, the perimeter, we have some of the diameter and all those physical measures of a malignant, whether a cancer is, breast cancer is a malignant or a benign. And one is basically whether it's a malignant, which is basically dangerous, and the benign, which also dangerous, but it actually stays in one place, right? So let's quickly answer learn dot selection for the train test plate. um I'll also need the model itself, right? For the logistic regression. So for also scaling the data, I will be needing the scaling, min max scaling. uh, we also wanted to, have some data about whether how much our model is performing good, like after you've done the model, we want to understand our model is good enough or not. So we'll be importing something called as a classification report, and yeah, that's it. So that's what we need. And let's just load breast cancer. So what we're gonna do is we're gonna take out the frame data frame itself. think there is some attribute called as true. Okay, so the data, it looks like, okay, it's a dictionary. Let me just get the keys. So we have the data, we have target, we have the frame, which I believe is basically the, the same thing, and we have description, file name, data module. Right. So what we do is we try to answer, put it into a dictionary, right? And okay, I also need the names. X is basically the answer data dot get the uh, frame, I suppose. Yeah. So this X is basically in a data frame itself, and we also have the target here, right? Let me get the data once. What do you have the data? What we can do is we take the data out, store it in X, and then we also take the target out, answer data dict out, uh, get the target. I need to do it in this way. This is my X, and to see the Y, right? So before we do anything, I also wanted to check. So this is one of the important thing to check when you're doing the initial data analysis, whether, especially with respect to classification problem, that whether the data set is balanced or not. And how you do is that how many types of labels or class labels you have, you wanted to check how they're distributed. So it's very simple. You do a simple value counts, and as you can see, the data set looks kind of balanced, because if you see it's 357 and 212. It's not exactly balanced, but then I think it is perfectly fine. If it had been like 50 or 60 samples, or let's say 100 samples, then we have to do some artificial sampling. And also we can be doing something like a stratified trend test split. um, but in this case we do not need this, so that's okay if we just directly go ahead. So what we have done, we have the X and we have Y. Let us quickly do a split. So in this split, I just copy this part, right? We have X and Y. Train size is, let's say, 0.80% or 80%. S size is 0.2, and the random state, let's say it's 42. Okay, so we have done this um, splitting of the train and test. Then what we're gonna do is we gonna scale the data. Max is min max scalar, and we're gonna fit and transform. Fit transform data. Right. So this will be the extreme. Okay. So what we can do is we can see this, the return of this fit transform is basically a numpy array of extreme data. We can actually convert it back into a pandas data frame. It's quite simple. You can just pass it to the data frame class, and we need to specify the columns. So the columns will be same as the extreme, right? Uh-huh. So here we are. So now we can directly call the logistic regression class here. We can obviously do some fine tuning, but this is not the scope of this video right now. But yes, we can do fine tuning. Even we have this cross validation, logistic regression cross validation inbuilt. We can also try out with that to fine tune the model. With respect to this fit, we have the X train and the Y train. So the model is trained on train data. Let me quickly get the okay. So before that, we also need to do the scaling changes on the test data. So it will be min max C, and the same thing we need to repeat. So I'll just get the same code from here, right? And the log R dot predict my from X test. So now what we can do is we have done the training of the model as well as we have the prediction data. So we can actually call this classification report and see how good our model is actually performing. So we have the Y test data and we have the Y predicted data. Cool. So we can see our model is, if we see the first accuracy, it's performing good, and then if we see the precision and the recall, and also the F1 score. So F1 score with respect to zeroth class and with respect to one class, I think it's just doing good. Um, Let me also see this display 357. Okay, yeah, it looks good to me, and we are getting more than 90% of accuracy score. So yeah, so that is actually what we have with respect to the logistic regression. Now we can make a separate video on each of these metrics, when to use what kind of metrics, how to understand this data, and some more details about it. So please put your comment or feedback down the video, and if you need this video, separate video on this, I'll definitely make on that. And yeah, thanks.